Welcome to discussion on maximum power transfer theorem. This theorem is not just a mathematical curiosity. It answers a deep engineering question of, under what condition does a source deliver the maximum possible power to a load? To understand this, we must revisit core physical laws, KVL, KCL, and most importantly, energy conservation and impedance matching. Let's begin by building intuition from the physics up. At its core, power is the rate of energy transfer. In electrical terms, P is equal to V times I. Now imagine we have a voltage source with internal resistance connected to a load resistance. The total current in the circuit is I equal to V's divided by summation of RS and RL. Thus, power delivered to the load is I squared times RL, which is equal to V squared times RL, all divided by RS plus RL squared. We want to maximize this expression. But before we do, let's understand why the configuration matters physically. In the real world, every source has non-zero internal resistance. This is a manifestation of microscopic collisions and friction like loss in the source. If the load resistance is too small, most energy is lost inside the source's heat. If the load resistance is too large, the current is tiny, so the power delivered is also small. Somewhere in the middle is a sweet spot, a perfect balance where the energy is split between the source and load, allowing the load to receive maximum power. Let's derive it formally. Given the voltage source is Vs, the source resistance is Rs, and the load resistance is RL, power to load is Vs squared times RL, all divided by square of Rs plus RL. To have the maximum power, we need to take derivative in respect to RL. If we do it, we will have the equation shown on screen. To have maximum, we need to set the dP over dRL equal to 0, which means the denominator in the equation should be equal to 0. That will happen only if Rs is equal to RL. So power is maximized when load resistance equals source resistance. This isn't just algebra. It has deep physical roots. In transmission lines, impedance matching ensures no signal reflections. In RF and power electronics, mismatched impedance leads to standing waves and losses. In nature, maximum power transfer occurs when the source and sink are electrically balanced, not too greedy, not too passive. Let's say we have voltage source equal to 12 volt and internal resistance equal to 4 ohm. We want to choose the load resistance for maximum power. Using the theorem, we know that RL should be equal to Rs. If so, we will have 1.5 amp current, which means 9 watt power in load. Now let's change the load to 8 ohm. If we do that, now the current become 1 amp, which means we will have 8 watt in load. You see it decreased? Even if go the other way and change the load to 2 ohm, we will see that current becomes 2 amp, which means the power will be 8 watt. It's important to note that maximum power is not maximum efficiency. When load resistance and internal resistance are equal, only 50% of power is delivered to the load. The rest is lost inside the source. In power systems, we usually want low source resistance and high load efficiency, not necessarily maximum power transfer. We can use this theory for matching speaker impedance with amplifier output for best volume, or optimizing coil coupling to transfer maximum energy, or ensuring efficient transmission by impedance matching. To summarize, maximum power transfer occurs when load and internal resistors are equal. This emerges from basic physics, KVL, KCL, and energy balance. The theorem is powerful, but must be applied strategically depending on whether your priority is power, efficiency, or safety. You've now seen how physical intuition, mathematical proof, and practical examples all lead us to this elegant and universal engineering principle.